So hi everyone, my name is Shixuan Zhao from the Ohio State University. It's my great pleasure here today to introduce our project, Reusable Enclaves for Confidential Serverless Computing to you. And this is a joint work with Pinshen Xu, Professor Guoxing Chen, Mengya Zhang, Professor Yinqian Zhang, and Professor Zhiqiang. So before we dig into the detail of reusable enclaves, I'm going to first introduce some backgrounds and motivation of the project. And the very first question is, what is serverless? So in the old way, the traditional way you're going to deal with running an application is that you got to own your own computer, or like server or VM, you install your OS, you manage the updates. And sometimes you just want to run an app that's similar to Hello World. It's kind of heavy. But the problem is most of these applications are actually written in JavaScript or Python, this kind of standard language, and they got standard runtimes. That everyone is deploying the same thing, so why not just let the platform do it? And indeed, they did it. And they called it serverless because you don't really own a server. And everyone's doing it, like Amazon, IBM, Microsoft, and Google, they're all doing it. So a typical setup of serverless looks kind of like this, that you got a front end, which is a gateway that takes all the user's workload. And it's going to have a dispatcher, like workload balancing, going to send the workload to the back end where the executor is. And they got a runtime in it that can take the workload and just run it. So with serverless, they're going to be confidential serverless, and basically what they're going to do is that they protect, the most important part is that they protect the runtime within an enclave, and so that the user's execution can be protected. But for either serverless or regular serverless or confidential serverless, they all suffer from one problem called code stop problem, and the root cause is basically still about the executor. If you look at the life cycle of an executor, you see that you first deploy one, so it gets set up. And after it's ready, it takes user's workload and gets executed. And finally, it returns the result. But what happens next to the executor? So the trivial way to do it is obviously to relaunch the whole thing. You just kill the executor and to deploy a new one. But that is very heavy. If you look at the penalty, you can see that we got some facts here, that in the industry, the median memory consumption of a serverless workload is about 170 megabytes. And 50% of the workload ends within 1 second. But here, like for example, we talk about confidential serverless. Here's an Intel SGX enclave size versus launch time. You can see that for 170, it takes around 2 seconds to launch an enclave. And that's 2 times longer than the execution itself. So instead of actually relaunching the whole thing, people came up with the idea called keep the environment warm. That's a reuse environment. And for regular serverless, people came up with 2 types of ways to keep the environment warm. One is to keep the whole environment, including the user code, as a container, so that when the user code is called again, it will be reused. And the other one is to use a resettable runtime that, for example, like Python or JavaScript, their runtime most likely to clean up the whole environment after an execution. So you can just redeploy a new workload on it. But the problem is they don't quite work for confidential serverless because the first one takes precious enclave memory, and the second one, the runtime is relatively complex and large. They can contain bugs. So if there will be a malicious user that deploys a malicious workload that inserts a gadget into the runtime, the next user will no longer be a user but a victim. So for us, we also question that can we, instead of resetting, let the runtime reset itself, can we just reset the whole enclave? And yes, we think that's a solution, but it comes with non-trivial challenges. We have 3 challenges right here. The first one, how to reset. The second one, how to prove the reset. Remember, this is serverless. You need to prove the thing to the end user. And the final one is how to secure the whole thing. So the 3 key techniques to solve the 3 key challenges are the enclave snapshot and rewinding, nested attestation, and multi-layer intra-enclave compartmentalisation, MLIEC. So remember, this is going to be generic and architecture-independent method. It's going to be in software, but to give you some demonstrations, we're going to use x86 as example. So for the first technique, enclave snapshot and rewinding. Basically, when we talk about reset, we mean bringing back the enclave to a known good state, and that's basically about snapshot and rewinding. But not any snapshot. So what does snapshot need? We already talked about that the snapshot must be small because the enclave memory is precious. And it also must be fast to rewind because we want to solve the code stop penalty, so it must be fast. So our observation is that at the beginning, when the enclave just deployed, the stack and heap are actually empty, so they're just zeros. And the .text part, which is about the code of the runtime, is read-only. So for now, it's read-only. And .data and .bss segments actually contains the real data that we need to back up. So we propose a new reset module that adds new 2 segments that copy these 2 segments as the snapshot. And the running is relatively simple. You just copy them back and zeroing out the stack and heap, so the enclave will be ready, will be back to its original state. And with the reset, we now want to prove to the user about the reset. And also serverless, so we need to prove to the user their workload has been properly deployed. But typical enclave attestation, they are just boot time only. They attest the initial state of the enclave, but not like the thing we discussed about. So how do we prove the reset indeed took place? And the reset is correct, and about the user's workload. So we propose the way called nested attestation because it's nested within an enclave. And we add new 2 segments, which is a new attestation module that has a public-private key pair in it to sign reports with reset info and user payload info so that the user reset can be, so the user can verify it later. We now are able to reset the enclave and prove the reset, but the problem is they're not secure, right? So we're still facing that buggy runtime inside the enclave. It is all right for it to access the data above it, but below it, if it touches the snapshot and the critical data like the public-private key pair, will be so dangerous. But we can see that it naturally forms into layers, right? It actually naturally forms into layers. So if we only allow the runtime to access the data above it instead of below it, then the problem will be solved. So we're going to use software fault isolation. So the method is inspired by SGS Shield, and we use compiler techniques to achieve this. So the first 2 methods are borrowed from SGS Shield, called shared memory access and line branching. And for shared memory access, which we put a boundary right here, and we only allow rewrite above the boundary. So it is done using compiler instrumentation with these steps, and you can see we reserve the register R15 as the boundary, and we calculate the offset, make sure it's positive to access it. However, it can be easily bypassed by branching just to the final instruction. So we need to prevent this. And that's why there's a line branching, that we meet the code into blocks, into these fixed size blocks. For example, here's 32 bytes. And we align all the branching targets to the beginning of the block so that no one can jump into the middle of the block. And we squeeze all the instrumentation into that block so it cannot be bypassed. So it's just, the instrumentation is quite simple. It's just align the address. But not all functions can be instrumented like that. Like sometimes we got security issues. Some instructions are quite dangerous, that instrumenting them will not fix the security problems, like boundary setup or read-write execution permission granting. And for some of them, like memory copy, is performance critical. You don't want to instrument it, otherwise it will cause severe performance degradation. But we found that for these functions, they are usually small, and with checks and main logic executed together as a whole, we can protect them without instrumentation, and that kind of falls into the control flow integrity. But conventional control flow integrity, they use trap and check. They meet labels and tokens, and they check them is quite slow. So we found that we already aligned all the branches, and that means you can't branch, a malicious code can't branch to unaligned targets. So what we're going to do is we move the function a little bit unaligned and put a bomb, which is an instruction that will cause the program to crash at the beginning of each of these blocks, so that if it's branched from the outside, the program will just crash. But in the inside, we chain them together with direct jumps, so the function will just execute as normal. And also, as we said, we have multiple layers, forms into layers, and how we do that, and why we do that, because of the least privilege principle. So that the attestation module is higher than the reset is higher than the runtime in terms of trust. And we do it by naturally forming the layer using linker script to arrange the layout. So far, we think the code is static. We said the runtime code is read-only, but actually that's not enough for serverless, because for serverless, there's ahead-of-time compilation that compiles bytecode to native binaries, has good in performance, but may contain any code or instructions. So we found that we already have the compiler toolchain. We can just compile the workload using the toolchain, so we can secure everything, except for the rewrite execution granting function. It's still quite dangerous. So what about the checks to it? Of course, we protect it using unaligned critical functions. But what are the checks? And what we're going to do is that we disable it before the user code execution until the next reset, so the user code cannot hijack this function to do bad things. We implemented the thing, so far it's about design. We implemented the thing using LLVM, Intel SGX, OpenWhisk, and WebAssembly micro runtime. And this is the overall architecture. I suggest you to read our paper for more details. The total implementation costs us 10K lines of code. So if we compare the relaunch versus reuse, we can see that it's not even close. The reuse is almost invisible on this graph. It's just so fast comparing to relaunch. And because we have instrumentation, we use nbench to test instrumentation overheads. And if you just look at the geo mean, it's about 10 to 25% for different modes. They're quite acceptable. And finally, we compare it with existing projects like SFAST and ACCTE. You can see that they spend a lot of time on reset, on their relaunch, and our thing is just fast, just very fast comparing to them. So the conclusion is the reset benefits are significant, and we solved the code start problem in confidential serverless with reusable enclaves with 3 key techniques: enclave snapshot rewinding, nested attestation, and multi-layer intra-enclave compartmentalisation. So that's all for the talk. You can check out the code. It's already on GitHub, and check out the 3 labs homepage. I'd like to take your questions.